The Fibonacci sequence has captivated the minds of mathematicians and scientists, biologists, designers and architects for centuries. It's a simple little sequence, easy enough to generate, and it's also known as the golden ratio. Its ubiquity and functionality in nature almost make you think it's written into the creation of the universe. Now, let's take a look at the sequence and show you how easy it is to calculate. It starts off with the number 0, the next number is 1, the following number is 1, and you just add the previous two terms to get the next term. So our next one should be 2, and then comes 3, 5, 8, 13, not 11, 21, so on and so forth. And this is the famous Fibonacci sequence. Now, take for example this sunflower, which is found in my backyard. And sunflowers are designed in such a way that they pack as many seeds into the head of their sunflower. And this spiraling technique here is actually all these little seeds packed into that head, and it follows this pattern of the Fibonacci sequence. That's just one example of the many, many places in nature where this sequence of numbers can be found. But that's not really our study for today. Today we're going to be taking a look at graphing explicit and recursive formulas for sequences. So far over the course of the year, we've talked about both explicit and now recursive formulas for sequences. Today we're going to take a look at graphing those sequences. So let's take a look at example 1. You have 22 stones. You pile up every night. How many stones are in the pile after the nth night? We want to make a table of our values, find the first 6 terms of the sequence, and then graph those. So n is the number of nights here. We got 1 through 6. And then the number of stones, we're adding 22 per night. So we'll end up with here, and there's our numbers. Okay, so we need to plot those numbers now going along. Our x-axis here is our independent variable, or also known as our term numbers here. So n here is our term numbers because that's the number of nights. We have 1 through 6. And then along our y-axis here is our dependent variable, and this is going to be the output here, which in this case is the number of stones based on the nth night. So this is okay, once we have our x and y axis labeled and graphed, we can then start plotting these points here. 1 over and 22 up. And so on and so forth. Now, this is a discrete graph. Remember, there's not going to be a continuous line here because our inputs here are whole numbers. Our term numbers, which were the value for n, were represented by whole numbers, or the counting numbers here in this case, and therefore there's no values in between 1 and 2. They're just discrete values here. All right, let's take a look at example 2. We are asked to use this explicit formula, L sub n is equal to 18 minus 2n, and we want to graph the first 6 terms. So let's go ahead and find out what those first 6 terms are by doing n and L sub n. We have 1, 2, 3, 4, 5, and 6, and it looks like we're starting off with 18 minus 2 times 1. Well, that's going to give us 16. It looks like our slope here is just going to be -2, so we're going to go down by 2 each successive term. So our points here will be 1, 16, 2, 14, 3, 12, 4, 10, 5, 8, and 6, 6. Again, we're going to graph this on our x and y axis. Along the x will be n, our term numbers. So we'll label those for our first 6. And then along the y axis is going to be our L sub n in this case. All right, once we have our axes labeled, we can go ahead and start plotting our points. Our first term started off here at 16, and then we dropped by 2 each time. Now, the final part of this, it says we want to graph this using a domain of real numbers. So remember, a domain of real numbers includes fractions. I'm going to change colors here now. Graphing the sequence, or graphing this explicit formula, I would end up with a discrete graph. Now, graphing a domain of real numbers, I'm now going to end up with a solid graph here, or a continuous function. because that will contain all numbers in between these integer or whole number values. So it says which graph is discrete and which one is continuous. The continuous is when my domain is equal to all real numbers. However, the discrete graph is when my domain are just my counting numbers or my natural numbers in this case, or I could say they are my whole numbers. All right, in example 3 here, we see a mathematician proposes a sequence to study properties of multiplication, S sub n. We're going to let S sub n be the nth term, where we have our first two terms, our 2 and 3. We're going to begin our sequence with the third term. Each term is found by multiplying the two previous terms. So writing a recursive formula, remember our recursive formula gives us statements. We're going to start off with S sub 1 is equal to 2. And we know our second term in this case also is S sub 2, which is 3. And then any term following is going to be the two previous terms multiplied by each other. So that will be S sub n minus 1. And we're going to multiply that to the term S sub n minus 2, where S sub n minus 2 just represents the second previous term. All right, now let's go ahead and find the first 6 terms of the sequence. We know our first two are 2 and 3. Let's just back up. We know our first two are 2 and 3. And then 2 times 3 gives me 6. 6 times 3 is 18. 6 times 18 is getting a little bit larger now, 108. And then finally, our last one is 1,944. So here is our first, second, third, fourth, fifth, and sixth term. Again, on our x-axis, we're going to use our term numbers. And then along our y-axis here will be the product, or this S sub n. Okay, once we have our axes labeled, we can go ahead and plot. Our first term is 2, our second is 3, our third is 6, our fourth is 18, and then after that, we're really off the chart here. So we're way up here at 108, and then for our sixth term, we're way up here at 1,944. Okay, in our final example for today, we are asked to graph the first 6 terms of the given sequence. So again, we're given a recursive formula. We have our first 2 terms, 8 and 6, and it says the next term can be found by taking the second previous term and subtracting the first previous term. All right, so in this case, I'm going to say that my third term will be equal to the first term minus the second term. So 8 minus 6 results in 2. Now let's go ahead and find the fourth term. The fourth term would be a result of taking 6 and subtracting 2. That will give us 4. Then we'll say 2 minus 4, and that will give us negative 2. 4 minus a negative 2 brings us to 6. Negative 2 minus 6 gives us negative 8. All right, here are our first 7 terms. Your job will be now to graph this on your XY axis.